Assalamualaikum and hi. My name is Nur Asmira binti Ahmad Zawawi. Metric number CF240060. So today I will be presenting my mechanic of material project titled Structural Analysis and Stress Evaluation of Roof Purlin based on the given civil and structural construction drawing. Mechanic of material focus on how structural member behave and when subjected to different type of load. In this project, a real civil and structural drawing was provided and we were required to analyze one structural member using mechanic of material principle including internal forces and stress evaluation. The objective of this project are first to interpret a real construction drawing, second to idealize a structural member into a simplified model, third to calculate loads, internal forces and stresses, finally to verify the safety of the selected member using allowable stress criteria. Next, the structural member selected for this analysis is roof purlin. The roof purlin is part of the roof framing system and span between rafters supporting the roof sheeting. The primary function of the roof purlin is to carry roof dead loads, live load and its self-weight. These loads are transferred to the rafter and then to the main structural frame. For analysis purpose, the roof purlin is idealized as simply supported beam. The loads acting on the beam are assumed to be uniformly distributed along the span. The following assumptions are made. The material behaves linearly elastically, loads are static, plane section remain plane after bending and self-weight is included. These assumptions are commonly used in preliminary structural analysis. The total uniformly distributed load consists of roof dead load, roof live load, and the self-weight of the purlin. The combined load acting on the beam is 1.5 kN per meter. The beam has two unknown reaction force. There are two independent equilibrium equations available. Therefore, the structure is statically determinate and stable, making it suitable for analytical solution. For simply supported beam under uniformly distributed load, the reaction at both supports are equal. Using equilibrium equation, the reaction force at each support is calculated as 3 kN. The shear force at any section of the beam is determined using the shear force equation. The maximum shear force occurs at the support and has a value of 3 kN. The bending moment varies parabolically along the beam length. The maximum bending moment occurs at the mid-span and is equal to 3 kN. This slide shows the shear force diagram. The shear force decreases linearly from the left support to the right support and crosses zero at the mid-span. This slide shows the bending moment diagram. The bending moment is zero at both supports and reaches its maximum value at the mid-span. This slide summarizes the maximum internal forces and their location. The maximum shear force is 3 kN, occurring at both supports. The maximum bending moment is 3 kN, occurring at the mid-span of the beam, which is 2 meters from either support. The maximum bending stress is calculated using flexion formula. The resulting maximum bending stress is 8.8 MPa, which occurs at the outermost fiber of the beam. The maximum shear stress is calculated using the shear stress formula for a rectangular section. The maximum shear stress is 0.35 MPa, occurring at the natural axis. A safety factor of 1.5 is applied. The calculated bending and shear stress are lower than the allowable stress limits. Therefore, the selected beam section is structurally safe. For stress analysis, a solid rectangular steel section is selected. The beam has a width of or thickness of 80 mm and a depth of 160 mm. For bending stress, the distribution is linear with zero stress at the neutral axis and maximum stress at the outer fiber. For shear stress, the distribution is parabolic with maximum shear stress at the natural axis and zero stress at the top and bottom surfaces. The result match theoretical behavior with a linear shear force diagram and a parabolic bending moment diagram. The calculated stresses are relatively low, indicating adequate structural capacity. The assumptions are reasonable for gravity loading. Although a rectangular section was used for academic simplification, a real roof purlin typically use C or Z section. In conclusion, the roof purlin was successfully analysed using mechanics of materials principle. The internal forces and stresses were evaluated, and the selected beam size was found to be suitable and safe under the applied loading condition. That's all from me. Thank you.